Okay, welcome everyone to our second talk today. The talk will be given by Professor Mikito Koshino from Osaka University, and he will explore Moiré. I don't even know, still we discuss how to pronounce it, Moiré, with the E or no, 2D materials and topological quasicrystals. Let's welcome our speaker.
Thank you very much. This is Moiré. So I will talk about. So actually, I'm a theorist, and I've been working on 2D materials. And the recent 10 years, Moiré is one of the main topic, in my case. So today I'll tell you about. This is a half tutorial. Yeah. So twisted bilayer graphene, maybe not all people are familiar with it. I have explained. So so the twisted bilayer graphene is just a two graphene layer system, but stacked in this way. So some rotational, with some rotational. So you would have some long wavelength heating pattern. So this is Moiré. Okay. So this was at first. So this kind of system was already noticed in very early stage in graphene research, but the people didn't care about it. And some research people just started work on like about 15 years ago, and they are actually conflict balance structure. And everything changed after the discovery of the superconductor system. This system in 2018. So then many people felt this jumped into the field. Okay, so this is the big change. And also not only graphene, we also have twisted transition metal that chalcogenide. So this is a different kind of 2D material. Again, we can make this Moiré system by stacking with some rotation angle. Interestingly, they found some fractional quantum Hall effect without zero magnetic field. So that then they are the very phase so works as a magnet. Okay. So now that this is a very big thing in this field, 2D material field. Okay. So this is the half tutorial. So so the paper. So family of 2D material. So we also have many different. Of course, just we can make more system just stacking 2D material with some incommensurate manner. So many versions are there. Like twisted bilayer graphene, also the AB with the stack or 3-layer system in graphene HB and the hexagonal overlaid. This is another important 2D material. So this is TM. This I already mentioned. Or in somewhere in the zone. Okay, so the many people are working in this field. So I talk okay, so physics of Moiré materials and field. The first part is tutorials. Moiré, how to simulate the electron band structure in this complex system. So this is called continuum. I've shown some band calculation, the example band calculation with bilayer was twisted. This interaction metal by control. So and also I talk about lattice relaxation of the system. So this is very important for electronic structure as well. Last, this is our recent work. I talk about one tri-layer system. What happens with 3-layer form? So more electron band. So Moiré period is very sensitive to that. So this is like this. Also, if you go to the small twist angle, then this L is period. The period becomes greater and greater, inversely proportional to angle theta. At 2 degrees, for example, is like 7 nanometer. And I think in this unit, so you have like thousands of them. Even the number increases if you go to the small twist angle. So that's very complicated system. Okay, so it's very difficult to deal with many atoms in units. So people usually do smear the lattice structure. They extract a continuum model. So this is like a schematic. So we originally, of course, we have some honeycomb lattice, but in some way we do some sort of coarse graining, and we end up with some continuum equation.
Question: is there always a periodic pattern for any angle?
No, actually, so
What's the
so
condition?
this looks like a periodic, but the atomic structure here and here not identical, because the Moiré lattice and atomic lattice are generally commensurate.
Are there some angles where it is?
Yeah, and some special angles, then they match.
What is the condition?
This is the some there is some mathematical condition. But this actually it turned out to be not very important. Atomic commensuration actually doesn't affect them more than. So in this approximation, we completely neglect such a commensuration. Okay, so it takes some time to explain how to extract the continuum model from the scratch. So I'll just explain the result. So it's very easy. So now graphene, if you consider graphene, now the low energy electronic structure is dominated by the Dirac, which is located at the Briançon core, not gamma. If it's a gamma point, the result is trivial. But because it's located off center point, then it gives many interesting. So now the graphene Dirac on the up top layer and bottom layer are interacting when two layers stack. So how to interact can be captured by this kind of picture. Just arrange. This is the extended Briançon. Then you have a Dirac at each of the K cluster. Okay. So layer one. They are all the same thing, but actually duplicated. So those white circle is a Dirac cone of another. Yeah. So they are just duplicated. This way. Okay. So we just overlap to honeycomb K-space honeycomb lattice this way, and draw a Dirac cone at each corner. Okay, like this. Black one in layer one, and then gray is layer two. Okay. So now you see the black and gray are actually, as I said, this is just a replica of the same thing. But you can see that it's arranged in various different K-space shift. Okay. So actually those distance actually meaningful. For example, if you have here to here, and then you have some intersection in some. And if you switch on the interlayer coupling, then you have some open a small gap, then bound a hybrid. This way. The point is you have many shifts. Okay. So if you take only the three corners from the center, it looks like this. So black one is interacting this, Dirac on this, Dirac on this, Dirac on there, on the same thing. And there's open the up again. So this is the K-space picture. So you can do the same. This is the same picture. This is the black Dirac cone, and this coupled to the three layer two Dirac cone this way. This is actually this distance, this distance, that distance. And again, this gray one is coupled with three negative shift. And if you do the again and again and again, and you have some periodic structure, then you can define the Moiré. Okay, so this is the periodic. But of course, you have the different distance. Okay, so if you include all of them, then you have a black and gray circle infinitely, and it's just this picture being all black. Okay, so that means the system doesn't have any periodicity. Okay. The point is the interlayer coupling, that coupling gray and black Dirac cone actually depends on the distance of the from the center of the cable. This is stronger here when closer to the origin but it's become weaker and weaker when you go away from them. Okay, so it's like this. This just schematically depicts the strength of interlayer coupling as a function of function. Now you can see that those are particularly strong. Okay? But they are actually exponential down. They're relatively small, actually 100 times smaller. Smaller and smaller. So then we are allowed to do approximation taking. So that's, and we end up with this. And then we can define that more. Okay, so we can treat the system as a periodic system. This is the way how to neglect the information. If you take everything, then the system will go. Okay, but this is further hopping is irrelevant. Okay, so anyway, so we can okay, so this is our how the system or our equation looks like. So this is a 4x4 matrix. This H null means direct Hamiltonian. Okay, this is another. So U is an interlayer coupling. It has three independent wave vectors, so that actually corresponds to that shift. Like this, omega is just a cubic root. Like this. So this is very beautiful. So it's very easy to solve it. So if you give a twist angle, then you determine these distances and it comes. That's it. Okay. So if you calculate the bound structure using a model like this, it's a different twist angle. 1.47, 1 degree and 0.8 degrees. And in a large angle, actually, you will have some remnant of the Dirac. So this was actually the Dirac pointed black cone and gray cone. And so they're hybrids. So, but at a certain angle, you can see that the central part where the film energy lies become completely flat. So this is called magic line. And flat band, so actually there are 8-fold. We have the original, this is 2 bands, right? 1 electron band, 1 whole band. And this set exists every speed valley signal. You have spin up and down and valley K and K prime. And at the end, we have 8-fold digit flat band. If you go even smaller angle, then some dispersion actually comes back. Okay.
What is on the y-axis? Is it the electron
Y-axis
volt?
okay, so electron volt.
Okay. Yeah. And if I remember correctly from last week's talks, there was statements that this band is not exactly flat, but has a very narrow milli-electron volt order.
Exactly.
So is that here also the case, or this was
yes, it's you have some small.
So this approximation which you did doesn't keep an exact flat band, but an enormously narrow flat band.
Narrow, very narrow
band,
yeah.
Right?
But you have some chiral limit. So this, if you neglect some part of matrix element, then the system becomes chiral symmetry. Then you have exactly flat band.
Symmetry will produce.
Can I ask a question?
Sure.
So here, the band structure looks like it is drawn over a periodic Riemann number. Am I right?
Yeah.
So in the previous slide, we were talking about the effective Hamiltonian, which is a continuum Hamiltonian. So how do we get here, like from like continuum piece to periodic piece?
It's key, okay?
Yeah.
So you have the 3 vectors. Those actually correspond to this and this and this. And you have the periodicity. Moiré zone, reciprocal wave vector of the Moiré pattern is like Q1 plus Q2. Sorry, Q1 minus Q2, Q2 minus. So there is actually a trick. So those Dirac actually shifted. Yeah, but so that originally those 3 terms are actually periodic. This is 0, and this is one of Moiré G vector. It's another Moiré G vector, and those are center shifted by one of this Q. Okay, But this is complicated. We merge two Dirac, and then the Q becomes 0. Then those three wavelengths change. But that's the originally. The original structure disappeared when it's connected by unitary transformation. I skipped on this one. Yeah, anyway,
So I still didn't understand that. Maybe you can explain it to me. So you keep actually the number of bands as you explained initially as they come from this new lattice structure.
Yeah.
About 50, 100 bands or whatever, right? So this is the number of bands which we see here.
Yeah.
Corresponds
It's just a part of it.
It's a part, there are
Yeah.
probably even more.
Okay, so
Right.
yeah.
So what is actually again then, so it looks like a full diagonalization, maybe with some approximations. Where is this again continuum approximation entry?
Okay, so this is because we forget about the handcom like this. We replace original graphene band structure with just Dirac gone. Dirac gone, yeah, it's like this. Okay, so that in the huge actual tight binding model, for example, it ends somewhere, far away. And we express approximately we have just infinite gone and just that we need cut off somewhere. Otherwise, we can then we get a finite dimension matrix. High energy, low energy, we can neglect those until graphene state doesn't cut at the low energy. Yeah, that's what.
And that's supposed to describe the reality close to the Fermi energy.
Yeah, yes, exactly.
Sorry,
Yeah.
what is the number of louder? Bands.
What is
Controlling the number of bands.
controlling?
I mean, from this three,
Okay, so the actual number of band, I don't know, but the cutoff energy is like 1 electron volt. So we have cutoff energy. Then the structure is not reliable. Yeah, we can increase the cutoff little by little. Then those part is already converged, but don't change. But that part of it will change. So this is an experimental part. Actually, if you have a flat band, then the electron interaction will very much ends. Then the superconductivity is formed. So now that's good.
So since it's not exactly flat, but anomaly narrow,
Yeah.
what controls this anomalous narrowness? It's like a small parameter which is still somewhere in the system. What is it?
Well, okay, so for example, if you go to some chiral limit, then the band is exactly flat.
So it's a distance from a chiral limit.
Yeah, distance chiral limit is I mentioned before, but there's some parameter. So this is yeah. So the twisted bilayer graphene becomes superconducting, but at very low temperature, like 1 degrees, and then sensibly becomes of the twisted. And because of you have a nearly flat band, so if you think electron interaction actually split down. It's kind of what I call Feynman. You have many band, and you have actually the correlated insulator. This is the actually band insulator, original. Here. -4 the filling factor. So this corresponds to the picture. Okay, so this is A4 digit, right? So this is -4. Here, this is. You go from here to there. Originally, you have a band, and here, this is here. But those parts actually the flat band region that they're simultaneously split depending on the number of electrons, and you have some superconducting some here and there. So I don't go very much detail. So this is the. Okay, so now the people are still discussing about the origin nature of this.
What do you exactly mean by term correlated insulator?
Correlated insulator.
What's the difference with
Band display, because I think, yeah. So this is the, I'm not inventing. Anyway, I understand the original. So those electron density, it's a partially filling. No band gap in the one body picture. But once you feel this, there are 8 bands here. If you feel like 1 band, 2 band, 3 bands, 8, and every integer filling, then those bands are automatically split, and then you have the gap. The gap is induced by the electron interaction.
Yeah, sorry, but there's no a direct signal of the splitting of those bands. If
Yeah.
you look at the spectrum, it's not very clear. So, from my understanding, the correlated insulator means the insulator we don't know very clearly.
Yeah, we don't get.
Yeah.
I think it's sorry. Yeah. I'm not an expert. Thank you. Okay. So we also have a transmetal dipole Moiré structure. It looks like this. This is a 2D material, but you have a this looks like 3 stories. And the band structure is very much different from graphene. So there is now direct cone is gapped. If you have a different sort of atom here, it gives a mass to the direct cone. Also, the molybdenum atom has a very strong spin for the coupling, so that we have spin really. So that's gap with few. Okay, and yes. So now, but Moiré, we have this basically the same thing. From top view, it's just a honeycomb like this. So it's exactly the same as the picture. And we can have a similar type of configuration in this twisted system. So basically, this part is very important. So this you focus on the Moiré band. So this is monolayered. Okay. So those bands are so this is K by this K by Moiré. Superlattice, they're not mixed. So just this part is folded in the small superlattice realm zone, and it has many meanings. Okay. So now in this regime, so system looks like this. Basically, this is just a K minus K squared because this is just a whole type probability. Okay. This is the bottom here. The point is, those we have 3 different Moiré effects. One of this delta large D is just an interlayer coupling. This is just basically the same as the with the volume. But new thing is we have this some on-site energy top and bottom because the energy gap between here and here actually slowly depends on the stacking nature. So this doesn't exist in back structure. So if you consider the local bound structure of this stack, this stack will be different. And you can calculate this local bound structure, then it turned out the gap size is actually different compared with the stack. So that means that if you have everything in one system, then you have this bound topological moves up and down slowly depending on the position. So this is actually similar like that. I know there is big debate about the reliability of the system anyway. So this is okay. So you have 3. So delta. Then in the SU2 form, you can those different deltas can be in like a XYZ type vector. This is power matrix. So that means that soon spin SU2 Zeeman field. Yeah, it looks like a local magnetic field of force. Okay. So this is the system. And if you calculate bound structure, it's interestingly, so we have, okay, this is medium bound, as I mentioned. Every band has a Valley-Chen number. The Valley-Chen number is, if you take just single value, and then you have some trivial Chen. because of the time Russell symmetry, the opposite value always have opposite chain number. But those nearly flat band actually just split by the electron electron interaction, then we actually have just random levels. So this is very important. So many people actually working on it. So
Can I ask a question?
sure.
First, maybe you explain it. Why theta is depend on R? I mean, this is the gap size, am I right?
Okay.
Uh,
So if you have Fermi, okay, so that just okay, the Moiré system basically is a different stacking and exists at the same system, one system. So here
Okay.
you can think about
Okay.
A stack. No, this is not
Okay.
okay, this is it. Okay, this is it. So you can call the bound structure, local bound structure. And then you actually plot as a function function. Then
Then my second question is that I mean, if you just rotate very small, then two SP,
rotate with.
two TMD,
Yeah.
very small. Then if you go to next slide, I mean, they have an opposite speed. I mean,
Opposite speed.
I mean, does it change the? I mean, do we need any spin orbit or not? I mean, or physics is just spin polarized physics. Am I right? I mean,
Yeah.
but here if you are okay, they are in different values.
Yeah, so yes, so the K value, if you stack it this way, so K value of layer one interact with K value of layer two, then upspin and upspin.
Okay.
But the interesting thing happens when you rotate 180° plus epsilon. Then now the upspin and downspin are interacting each other by more. And then it gives a completely different bound structure. Yeah.
But we need a spin orbit to couple them.
Yes, sure. Yeah. So now this flat band looks like a non-zero Chern band. Looks like no, it's Chern band is non-zero Chern number, and this looks like some sort of random. And you can calculate the effective magnetic field of those electron fields, and it's very localized. But anyways, in one more unit cell, it gives one magnetic flux. So that gives a very strong.
Yeah, there's another question I have again. Coming also from the talks from last week. So what does it really mean, this analogy between this observed non-zero Chern band and the Landau level? What do we mean by that? That it's roughly
Okay. So there is a mathematical transformation from here to. So there is some so-called adiabatic approximation. So now that you have some two, this is we treat this as a spin degree of freedom. We have a whole band spin up and down, then interacting with some local zero field. That direction actually depends on the position. Now, think about the limit of a very long range. Then actually you have some transformation at every single point. You just rotate that direction of the local z field up to the z direction. Then you have some top band. It's aligned as the stigma field and anti-parallel on the bottom band. Okay, and then you have some two band. Okay, so that if you do this is a position dependent unitary transformation. So that you do the unitary transformation, then this part actually disappears because spin is aligned in z direction. You have a plus something and minus something, and that part is a unitary transformation. You position dependent u times this and u double. And this turned out to give the magnetic vector function, P plus EA squared life. The A gives and if you calculate the magnetic field by taking rotation, that A vector function, then you get that. So this is the way. So this is a good approximation when this change is very smooth.
Is that also an approximation which here will give you an exact flat band?
Exact flat band.
Because the Landau level is exact.
Yeah, it's a flat band.
And here you still have a small dispersion.
Yeah, this is
So, but here now you do something. Here and you see
so we have some neglecting, so that actually gives a modification from that. Yeah. So there is a way to measure how close to the real number. Yeah.
Yeah, but I think the real number, this artificial number level is not exact flat because of the magnetic field is not uniform.
Sure,
Right.
sure.
Yeah,
But
so that's-
there's some argument, even though the magnetic field is not uniform, and but if your flux is one,
Right, right.
then you get actual.
You will get the same number.
flat.
Yeah. Oh, you get still get exact.
It's the exact flat, but because it's the index theorem stuff.
Mhm.
Yeah.
Sorry, let me ask you a question just to check if I understand correctly. The difference between this system with the bilayer graphene is the existence of this pseudo-spin-Zeeman field, which
Yeah,
makes
you
the.
also have the big mass gap here.
I see. I
There's
see.
two things.
These the two things that give the finite Chern number and this.
Yeah, so you have a C2D symmetry, then you are allowed to have the check.
I see.
This diagonal Hamiltonian is not R dependent. Am I right? This diagonal.
This one.
Then
Dependent.
by VR
Yeah, this one, yeah.
is not R dependent.
Is this R dependent? R dependent. Yeah, this because this is the position dependent gap, half of gap size, or something.
No, it is a single layer. How, I mean, if you consider
Okay.
second perturbation, it can affect it, but
For example, if your gap size is something, for example, then let's say delta, then the half delta comes here, minus delta comes here, because this is mass.
I agree.
But now that this gap size actually changes slowly with position, then that means that there's a position. This is by exploration. Yeah. So this is just a 15% of my time. Oh, no, Now, yeah. So the physical consequence of this is that you have actual bottom Hall effect like lambda one. If you feel the partial like 1/3 of that lambda level like thing, then people found some fractional quantum Hall. This is so surprising. So now that many people are considering why can we have this? Because fractional quantum Hall in the mass system only occurs very clean system. And also this is no lambda. So now the people are trying to understand. So this is very hot. Now, so this is second topic. So I changed the topic, the lattice relaxation. Okay, so this is actually very important. The lecture as a elegant bound structure. It's graphene. So now the many calculations done by assuming rigid honeycomb lattice. For example, twist bilayer, they consider the twist stack of a perfect honeycomb. But this is not actually true because the honeycomb lattice, this graphene is very soft, so the atom can move, and you actually have relaxation. So now that twist bilayer graphene composed of rigid honeycomb lattice is not really stable because it locally has a very unstable structure. Okay, as I said, the local structure looks like some parallel stack graphene with some certain shift. So this BA and AB are very good because this is graphite type stack. The natural graphite exists. Okay, so this is good. But the nature doesn't like this AA. The honeycomb lattice and honeycomb lattice overlap. So it's very well known in the community. It has a very high energy. So this system distorts spontaneously to reduce this unpaired variable. Okay. This is actually AA. AA is very high. Okay, how to do this? Well, there's some calculation. Now the atomic lattice picture is very complicated. Now I show just local stacking. Okay, this bright and high and low. Okay. And now I guess this is why The original, this is the non-relaxed rigid honeycomb. You can see that energy is very, very high AEA spot where the honeycomb lattice is completely over. And it's low in the graphite type. And after the lattice oxidation, it turned out this undesirable AEA part shrunk dramatically. This is how very small. And AB and BA part actually expand this way. Okay.
How was it calculated with some linear electron point?
Yes, this is we developed a continuum calculation. So that graphene elastic part is just calculated like as a continuum, usual elastic things to do.
And linear electron point.
Yeah. Yes.
Is this also experimental?
Yeah. This is very, very well. Okay. So now how graphene is graphene deformed to realize this structure? I'm sure. Okay, so this is graphene bilayer. And the point is this: if you increase theta, then the Moiré pattern should, of course. If you decrease theta, then the Moiré pattern expands. The actual system uses this to get this. Okay, so what is distortion? So AA, so originally it was bigger. So they want to shrink the A part. To do so, on this part, the two layers rotate oppositely to increase theta. Then it shrinks. ABB is opposite. So they actually moved to decrease theta. Then it displays. Okay. This is very important in the tri-layer system. Anyway, so that part, the oxidation effect is very important in the downstream. The non-relaxed cases, at some certain angle, this is non-flat actually, like this. And also, it's not like that, and the stick to the very close to the dispersive zone. This is the original calculation by the region. Honeycomb lot smaller. If you increase the relaxation, then the flat band part actually separated by the other part. And also it becomes flat. So the lattice relaxation actually helps the flatness, increase the flatness. So why? So so when they're doing it this, originally, there's more interlayer coupling actually between AB. So this is the coupling between the sublattice in layer 1 and layer 2. And you can see that AA part shrunk and the BA part is decreased. So that means that this part actually increased and the AA diagonal part will decrease. So this was is modified by this, and that means that off diagonal and diagonal part become have a different output. So this is the interesting. So if you go to this, the further limit, so this is actually chiral. If you completely neglect integrating zero, either get this diagonal part, that means the AA part don't need. Then you have a perfectly flat. So this is a chiral. Okay, so this corresponds. So that so that's just relaxation. So push the system toward the chiral. That's why you have a chiral. And in the recent paper, this thing can be explained by some anti-async index. So this is like a plot again manual. Okay.
And that is still 8-fold degenerate?
Yes.
I question, this is localized over AA center to this flat band linear function.
Wave function is somehow localized at AES. Very sharp. Okay. So we have a similar lattice relaxation, any type of Moiré system. For example, if you put graphene on hexagonal bond nitride, HBN is just a honeycomb lattice, but the A side is nitrogen, B side is water. Okay. Then you have some honeycomb lattice, different type of lattice relaxation structure. Because now the symmetry is broken, because the A side and B side have different output. So only one stack, this will have lowest energy, then it grows. Okay? In the graphene case, graphene case, this and this have the same energy, 180 rotation symmetry, and then honeycomb works. But now, okay. Anyway, if you overlap the twist TMD, and 0 degree case is like this graphene case, and you get the dry one. This here, this is and again, in this case, also lattice relaxation gives a very important example. As I said, if you do the calculation at some certain twist angle, and actually the turn band doesn't matter. This is trivial. Okay. If you increase the lattice relaxation, so the sound parameter actually changes, then the trip don't trip. So also the lattice relaxation assists the emergence of lambda.
On this transition from left to right, is that band somehow going through some band touching?
Yes. So this counter up and the touching and the turn number is distributed.
So this is a topological system, this one?
Yes, indeed.
each inversion is broken in the relaxation. And
The symmetry is the same.
symmetry is
Yeah, inversion symmetry is broken.
picking.
And then you say that in the very limit, you get a channel number, non-zero channel number, right? Or is that then? What limit? In the chiral limit.
Chiral limit. Chiral limit is very critical.
No, for you explained here when you had this lattice relaxation, you get in some sense in a limit, you would get at least this chiral limit, you would get an exact flat band.
Yeah, this is
Right, and my question is, will that still carry a channel number?
Answer is no, actually. So okay.
come?
So you have the many patterns. One is have +1 children. You remember? There is -1 children. So it's zero.
It's zero.
Yeah, it's the case. Yeah. Because twist bilayer graphene has C2Z symmetry. So 180 rotation in input. So this actually prohibits the emergence of graphene.
Use for twisted bilayer graphene, then you relax the AA part will shrink and the band will become flat, right?
Which one?
Twisted bilayer graphene.
Yes.
But for twisted TMD, it seems opposite. When you relax, this one.
Yeah, it's very complicated. Yeah, it's a different system. And flatness is not always as helped by the rotation. But it's very fast. Very complicated.
I also catch. Do you think about the right-wide rotation or left-right rotation commonly propounded in this case? Do you think about this kind of left and right?
Left and right hand has, I think they have the opposite valuation.
Yeah, but in the same lattice relaxation, some part is left,
Yeah.
some part is right.
Some part is left, some part is right. But then you have some domain wall.
Yeah.
I'll talk in 3-layer product. It's not. Yeah. Okay, try layers. So now, okay, so more superlattice 2.0. So now that everybody were working on the more bilayer, but of course it's basically very straightforward to make travel. A travel system is complicated. Everybody avoided to think about it. It's very complicated. So if you just randomly arrange 2, 3 layers, okay, layer 1 and 2 you have some sort of whatever, and from layer 2 and 3 you have some sort of, but they have no common period in general, of course. So if you overlap 3 layers, you have some funny, very complicated structure from the interference of the 2 random wire. So this is a very complicated system. One can think of some very long range pattern, so the energy scale is very simple. It's not relevant, not relevant, for example, what may think. But actually, there is a very regular physical tendency and some very relevant bound structure. So this is first example, the graphene case. It's the simplest. What is lattice? Okay. So this originally is like this. Okay, so if you don't do any relaxation, it looks like this. Now that this is not atom. So this red dot means the AA spot of one more atom. The blue dot is the AA spot of another one. Okay, so this is actually Moiré pattern of each neighbor plate. So without lots of relaxation, then the red one, blue one are period. So if you switch on the relaxation, actually those two Moiré lattice interact. Some interesting.
So maybe it is not clear. So is it the twisted pattern of dice lattice? This structure looks like. No, the right one.
Right one.
Similar to the twisted except dice lattice.
Yeah, dice lattice. But just try and just try. Is that this?
Okay.
Yeah, this is it actually. Yeah, this. If you have bilayer, you have this. The red part corresponds. You have two settings. Okay. So after the relaxation, I hope you see this. It's a non-relaxed, it's the same picture as the previous week. Now somehow the red dots and blue dots don't like each other, so they try to avoid, and they give some local conventions. So this is and here you have the similar thing, but this is just 180. Okay, so more and more. So how this occurs? Okay. Oh, this is another picture. This is just I plot the population of the local stacking. Local stacking in high A, low. Just we add over where I want it to. And it was after the relaxation, they have some rows of arranged in order to not overlap each other. So now that we can understand the reason for formation this way, all these domains are formed. Again, I hope you remember in bilayer case, they try to minimize the AA structure by increasing the local rotation. Then the pattern should. Okay? And AB and BA is opposite. So in trilayer case, they are trying to do the same thing. Okay? But point is, layer 2, middle layer is shared by Moiré 1 to Moiré 2, 3. So you have some sort of frustration. So for example, this is Moiré 1 to Moiré 2, 3. This complicated structure. If you overlap blue dot and red dot, what happens is layer 2 wants to increase the rotation, and 2, 3 also increase the rotation. Cycle 2, 1, 2. But if you just black moved in this way, then 1 is shrunk and 1 increases, 1 reduces. Right? So there is it's frustration. Okay, layer 2. If you move in this way, that's improve the Moiré 1 2, but this is disimprove the other. So this is bad thing. So that nature try to avoid red and blue each other. For example, red come to the center of the blue hexagon, then actually those frustration is resolved because of favorable rotation angle is opposite. So that's why they manage. So also the even interesting thing is this gives a very specific peculiar structure in the structure. Okay, if you just calculate this whole system, you can calculate it. And you have some energy gap-like thing, but the field with some sort of strain down, very regular down. Their density stays very, very low. but field is some state. So this is actually the very one dimension. But you take some certain one state that is like very one dimension. Like this. This is wave function with some certain states. This is actually you have three sets of current surface like this, and some of this, some other states. So you have the three sets of the one-dimensional channel.
This is real space.
Yeah, this is real space. This is case. So the y is here. Okay, so this is because now, as I said, you have some y domain structure from E and E alpha. They have, if you calculate the local bound structure, it's similar. It's almost same because but local channel number is different. It's about the whole complex. So it has a +1 as a -1 and this +1. And because of 180 voltage. So the different channel that automatically requires an edge state. So this is that. So we those emergence of those state are unavoidable. This is actually edge state. Here it really looks like an edge no bounded. So this last part, but just very short.
Excuse me, If we continue, I ask you maybe in general, not precise question, but what will be with these relaxation mechanisms in the presence of some point-like defects or some atoms on the surface of this structure? Can it change the physics?
Relaxation.
You discussed the relaxation of this like perfect structure, but if in nature we have some point-like defects in crystals or something else, how can it affect your results of relaxation mechanisms?
So I assume, of course, I calculate assuming the originally perfect structure. So if you have some point-like defect, then you can see that, in the experiment. So if you go to the relatively small one, like 0.5 degree. Then you just see the randomness of those triangle structure. Actually, you still see them, but it's distorted depending on the local strain. The point defect even gives a very strong impact. Here it is. But locally, it gives the structure. Yeah. The last part I talk just 2 or 3 minutes. Because this is just the same thing, but the graphene sandwich with HBN. So in the previous part is the graphene. But what happens if you sandwich graphene with HBN? It's again like 3-layer systems. But it gives a different. But if you think about first, the bilayer graphene on HBN. Graphene has the HBN honeycomb lattice, but it's different. As it's constant, it gives a more superlattice. Without rotating. Okay, so that structure is like this, and if this is a Moiré pattern, and the point is HBN is very insulating system, so it's gapped and a fermi energy. So low energy structure is basically dominated by Dirac cone, but graphene Dirac cone actually feels the extra superlattice potential from the HBN. Okay, so then the Dirac cone actually chopped into small band and they have band gap. So this is very well known and observed in experiment. If you change the angle, then so the Moiré pattern shrinks and its gaps actually go further away. The tri-layer, so now the HBN open the energy gap by superlattice. If you have 2 different Moiré patterns, then it becomes the 2 gap opening effect actually the conflict each other. They give some very complicated fractal-like gap structure. So it looks like Hofstadt as well. This is the 2 lattice in magnetic, but it's nothing to do magnetic. It gives a similar structure. Okay. Now Hofstadt butterfly actually this mathematical. This is 1D quasicrystal problem. You have 2 commensurate potential, then your energy gap is like because the red one and blue one is the energy gap in a different places, and if they have both, it's like this. Okay. Now, let me give the more push. Now, our system somehow the large two-dimensional version. Now you have the two-dimensional space, but you have the different periodicities. You have the four different wave numbers. And in one, okay, I skip. It's interesting. Now, 1D case. Okay, so you have the many gaps. So those things are actually topological because it's connected to the quantum host. So those gap labeling number correspond to the quantum host contact. Okay, so we have a similar mapping to the double field system. Then you can imagine you have some higher dimensional object, magnetic field, which gets explain the gap labeling. And we actually have this, and this is a 6D system, and we have a 4D quantum Hall effect in a subspace system. This is quantized by second channel. Originally, quantum Hall system first, but this is some imaginary effect, and this is second channel. This is some just an integrated of the interface time variance. Anyway, actually, those numbers actual levels, gap levels. So in any case, yeah, so this is the actual graphene HBM sandwich system. So every gap actually has a, we characterized by 6 second channel. That's how the direct connection, higher dimensional one. Okay. So there's 3 dimensional order. Okay, this is something. Okay, thank you very much.
Thank you very much for this wonderful lecture, Professor Koshino. We still have
These numbers, do they have some boundary correspondence or not?
Good question. And the answer is yes. And yeah, short answer is yes. So that if you cut the system somewhere, you have some direction. Then you can calculate the number of the edge states per lane by using the.
more questions. Yes, please.
Yeah, could you explain more about this 4D quantum Hall effect? So you based on this 2D system, and you need 2 synthetic dimensions to do it, right? So what are these 2 synthetic dimensions?
Okay, I'll explain. And so 1D periodic, so this is considered the relationship of the 1D periodic system in the 2D Hofstadter system, to the last. And to the last magnetic field, if you take the vector potential depending on x, then the ky is a good quantum. The system becomes just one-dimensional system with periodic potential. Periodic potential and then this period related magnetic field. Okay.
Right.
So we can do the same thing. If you now that we have a 2D system and actually 4 different periodicities. For example, if you have just 2D system in just one periodic sinusoidal potential, so you can think about okay, you can stack the layer and then give some hopping and apply the magnetic field in the plane direction. Then this is equivalent to the 2D system with the sinusoidal. Just the same. Now, our twisted complicated system is 2D plus 4 different periodic lines. Okay. So now that you can think about the imaginary direction Z1, Z2, Z3, Z4 on the top of X and Y. So then you give the 6 pieces. Then you put the magnetic field every direction. Then you get the exactly the same thing. Okay. So now now you have 6D system. And you can define the 6 different 4-dimensional subsystems like X, Y, Z1, Z2, or X, Y, Z2, Z4. And each 4D system is gapped in the system. And then you have some second channel, those 6 subspaces. That gives them, yes.
Thank you.
More questions?
Sorry.
I think very nice. I want to make sure that for bilayer TMD system, you showed many Chun-band. It's actually the Delhi Chun number, right?
Channel,
Yes.
yes.
You have a K and K prime
Yeah,
over the Chun number, right?
or cancel each other.
But you want to include the intervallic scattering. You have a quantum spin node state. Do you have a quantum spin node state?
Quantum spin holiday. Quantum spin holiday. Intervallic coupling.
They have a
You mean quantum spin holiday?
Quantum spin.
Yeah, that's you don't need intervallic coupling. So if you have put gap in somewhere, and then the whole current goes in this way for K, and that way K prime. This naturally gives a quantum. So you don't need coupling. Yes. That system is quantum spin Hall state. Not spin, okay. Valley, but valley is locked. Yeah, okay, the quantum spin.
quantum valley spin Hall.
Or valley and spin, yes.
Yeah, that.
And when the intervalley coupling included valley meaning, but
The valley coupling is included by some disorders. Then that actually breaks and bonus.
So I have two questions. So for those twisted MOT did you got it kind of some number plus one plus one plus one? Yeah,
plus one.
yeah. It's 2.1 degree rotation. So you want a fraction
Fractional quantum Hall.
version.
Infinite Mach isn't data. I think the lowest, I think they are using the lowest in Cherpa, having class. That's
But you, yeah, okay.
yeah. The different band basically correspond to different band number.
Yeah, but if there are different number.
Different churn number from the first band and second band. Let's talk later.
Because I have a second. Sure. For your quasicrystals, EN level, did you consider the interaction with the person?
No. Or simplest.
More questions?
I have one question regarding that, quasiperiodicity. So your theory about 3 layers show that, okay, we have a relaxation effect and it make some structure for this Moiré of Moiré. But do you have any explanation that when the relaxation suppress? I mean, if we have a system, we have a chiral stack system, we have a system that go to relaxation, and we have a system that they don't go to relaxation, and people call it Moiré quasicrystal.
Yeah.
So but I cannot understand when this relaxation happen and when this relaxation not happen.
Okay, so basically we are working on the commensurate system. So we assume a very big commensurate system because we cannot calculate the commensurate system. Then, so that it's commensurate from the beginning before we introduce the calculation. Then we have some wire system. But this infers what happened in the really incommensurate quasiperiodic situation, because now that we know that some tendency of the black, blue and red AES spot actually avoid each other. It's all there. So you can consider that if you even your system is quasiperiodic, so that thing happens and it gives us some local stacking structure here and there, but it's not pure. So this is my guess.
There was another question?
Yeah, it's kind of related. So in the tri-layer system, for the incommensurate angle, what is the system size that you calculate for the commensurate angle?
It's it's typically like 12 more period times 12 more period.
So for even for the incommensurate system, you expect some kind of this.
Yes. Yeah.
A and
So for example, yes, so for example, there is some for example. Yeah, this is actually the real period of calculation. You can see that the red one and blue one have very different periods. But it's, in their case, you still see the red one to come the center of the triangle. You can see that the structure is not conventional. You can see this part you have all 3 blue, you have 3 blue and 1 1. So that if you have a quasi-periodicity, something like this happens. So those structures not exactly periodic, but then locally they manage to avoid the red. Yeah.
More questions?
Yeah, the one short question, just a curiosity. If you consider the 3-layer system like a silicon, graphene, silicon structure.
Silicon, graphene, silicon, yeah.
Yes, then do you expect what happens? Can you comment on? Is it similar to the 3-layer graphene system or the boron nitride graphene boron nitride system?
Okay. Silicon has a similar symmetry with graphene. Yes,
Yeah, but there is some mass gap.
Yes, up and down. Okay, that's interesting. Okay, so now we have a triangular structure when the A B stack energy and the B stack energy are exactly the same. So then now the silicon has because the backlink, it's something like that. I just said HPM.
HPM.
Then I guess we should have a hexagon. Yeah, just guess. Yeah.
I see. Thank you.
Yes, please.
So in this tri-layer, what determines the length scale of the Moiré and Moiré? Do you take the percent?
Yeah, so this is just okay. Well, you have one more. This just the same as a Moiré period determined from the graphene. This is a higher version, and you have one reciprocal lattice vector of one Moiré. This is G1. Say G2 is like this. It's slightly different. Then the G1 minus G2 that gives a Moiré scale. I think.
More questions?
Yes, please.
To your question.
Gotcha.
Why people studying twisted bilayer, 3-layer, 4-layer, and more layer? I mean, if you go to more layer, there is something new that cannot happen.
Yeah. Interesting question. Okay. That's history. So now the people started work on concerning more system. Like the first paper come in 2008 or something. Very important flat band paper 2010. But I still remember that the atmosphere. Okay, you were working on such a minor, it's a niche thing. So this is what I was told. 2015 actually. Yeah. But then everything changed after the 2000 superconductivity twisted bilayer. Now that's really become very major. So now the experiment is very big. Now the twisted bilayer graphene is so interesting because the superconductivity never happened just a single layer graphene, one graphite. So this Moiré is very important. So that means the Moiré gives actually changes dramatically the original original matter. So now the people then do the TMDC. Then they found a fraction of the zero magnetic. This is surprise. So now they tried in something new in the heavy direction.
May I add another question to the same topic? 1 Kelvin is probably also common for other 2-dimensional structures. when it comes to two-dimensional superconductivity, or is that somehow a record? So if we go to other materials, 2D light materials, which show superconductivity, what are the transition temperatures there? What are the
By
methods?
far, there is a 50K.
Right,
Yeah.
so this is not really impressive.
Yeah.
Why is it impressive? Okay, so 1 Kelvin.
One game, yeah, many people. Yeah. It's like very small energy scale field. Yeah, but
Yeah, superconductivity maybe is not that impressive, but the fractional quantum anomalous Hall effect is very impressive. You cannot find anywhere else.
I see. Some people try to, okay, so the fraction quantum monolithic, so that there are one bilayer and super the quantum computer stuff. But an original gallium arsenide system is very, very hard to access because it's embedded in the interface. But now 2D material open. So you can do many different things. So in the program, it's called fractional time. Right. So I think this is the strategy.
Get a second one? No? Okay.
Maybe I will answer. When you talk about relaxed structure, then you do this perturbative calculation of like electronic and phononic degrees of freedom or some selfness. How do you get this relaxed band structure or
Band structure, okay, okay, so relaxation calculation is independent of the band calculation. So because this is basically determined by the elastic energy on the interlayer coupling, A, B. So we assume this very simple sinusoidal energy landscape as a function of the shift like A and B. So you need to just, okay, so you construct the system only giving them A, B, and AA energy and just minimize the total energy and you get some sort of. And then for the, now you know the where the carbon output and what is the interlayer registry. Then we calculate the bounds. So that part is not self-constant.
okay.
Yeah.
Okay, any more very important questions right now? If that's not the case, let's thank Professor